Okay, what we're going to be looking at here is a quick little practice problem for some gravitational forces. What we're going to be doing is we're going to be looking at how the moon, Earth, and the sun, I guess this is the moon, have gravity acting on themselves, or each other rather, and what that gravitational attraction would be given a kind of setup like this. We've got the sun here on the left, and these are all in a line. The moon, so this is a new moon right here, is between the sun and the earth, which is this circle with a plus sign in it. That's a green earth right there. And we're going to do this for two scenarios. We're going to figure out the gravitational force exerted on the earth and on the moon. And my hint for this is to draw some vectors in this problem. And we know a few things here. We know the mass of the moon is 7.35 times 10 to the 22nd. And we know the Earth-Moon distance is 3.84 times 10 to the 8th. If we check out our solar system data sheet that's sitting in the folder for the Google Classroom, we also happen to know a few other pieces of information. Let's see, we'll put this in pink. We know the Sun-Earth distance here is actually it's about 1.5 times 10 to the 11th meters. And we also know that the mass of the sun is approximately 2 times 10 to the 30th. It's 1.99 times 10 to the 30th, so might as well just make it 2. Let's see, we know the mass of the Earth is about 5.97 times 10 to the 24th kilograms. So now we know the mass of everything, and we know distances, because this is the moon-Earth distance right here, and we have the mass of the moon. So how are we going to do this? Well, let's look at Earth first. So if we go ahead and look at Earth, if this is our Earth, Earth is being pulled in this case by both the moon and it's being pulled by the sun. It has two forces pulling on it. And both of these forces are acting in the same direction. They're both pulling it, as we have it drawn, to the left. So because these forces are in the same direction, these forces are going to work together. Whatever each of these forces is, we're going to put them together, and they're going to create a larger force. So let's just figure out what those forces are. We know gravitationally that the force due to a gravitational attraction between two bodies is big G. That's the gravitational constant. MM, M1, M2. Sometimes, right, this is a big M, little m. Doesn't really matter. It's just the two different masses. So the moon and the Earth, the sun and the Earth, divided by r squared, where r is that radial distance away. It's just how far away are the objects here. So if we do this for the moon, we're going to have G. This is the mass of the Earth. This is the mass of the moon, divided by, and then what's the Earth-Moon distance? That is the, whatever the Earth-Moon distance happens to be squared. So we're going to put in the mass of the Earth, 5.97 times 10 to the 24th. The mass of the moon, 7.35 times 10 to the 22nd. G, if you remember, is 6.67 times 10 to the negative 11th. And then divided by r squared, or that r is the Earth-Moon distance right here, 3.84 times 10 to the 8th. So let's just crush that number real quick and see what we get. So 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th. I've got about 4 times 10 to the 14th, a little bit less, times the mass of the moon, 7.35 times 10 to the 22nd. So I've got about 2.92 times 10 to the 37th, and then divided by, and I like to put everything here in parentheses because I've got to square something, the Earth-Moon distance, 3.84 times 10 to the 8th squared. And I get that this number is approximately 1.98 times 10 to the 20th newtons. Okay. Now I have to do this exact same thing though, but with the sun. I'm going to set up the same thing. It's going to be G, mass of, and now it's the mass of the sun and the mass of the Earth, because those are our two masses here, sun and Earth, divided by the Earth-Sun distance. So 1.5 times 10 to the 11th squared. And I just run this number back through. So 6.67 times 10 to the negative 11th times 2 times 10 to the 30th gives me about 1.3 times 10 to the 20th times 5.97 times 10 to the 24th. We've got 7.96 times 10 to the 34th divided by parenthesis 1.5 times 10 to the 11th, close parenthesis squared, close parenthesis, and I get 3.54 times 10 to the 22nd newtons. Okay. Now, both of these are in the same direction, so I can add them together, and that will be our answer. So 3.54 times 10 to the 22nd plus 1.98 times 10 to the 20th is going to be our total force for part A. So our force per part A is just the sum of these. If we actually take a look at this, it's pretty much just going to be the 3.54. We could rewrite 1.98 times 10 to the 20th in terms of 20 seconds by moving this decimal over 1, 2. So this would be like 0.0198 times 10 to the 22nd. And since now these exponents here, or rather the times 10 to the power, are the same, we could just add up the numbers out in front. So 3.54 plus 0.0198 is really still pretty much just 3.55 times 10 to the 22nd. It really didn't change much there. Newtons. So that's our first force that we have here for part A. Maybe if you're like, oh, that rounds up, maybe you can become 3.56. It's really whatever. For part B, what we're doing is we're just trying to figure out the force exerted on the moon. And in this case, we don't actually have to do a whole lot of extra math. The only thing that occurred in part B with the moon is that the moon is between. So there's the moon, there's the Earth, there's the sun. The moon's just between the Earth and the sun, which means that the moon is going to have the same force that the Earth had pulling on it. It is still going to have this 1.98 times 10 to the 20th, because this force must be equal and opposite in both directions. The Earth is pulling on the moon is pulling on the Earth, they are equal. So we know what this value is right here. However, the sun is not pulling on the moon in the same way the Earth is. The sun is pulling on the moon this way. And we don't have this value, actually. We need to go find this value here. So we need to find the force between the sun and the moon. This is a little tricky to do because we're going to have the same G, mass of the sun, mass of the moon, over the sun-moon distance squared. And what we actually have to do to find that sun-moon distance is we need to do a quick little subtraction problem. We know that the Earth-sun distance is this 1.5 times 10 to the 11th. We need to subtract off of it this distance right here, which is this, in order to figure out what that sun-moon distance is. It's not going to change a lot because that times 10 to the 11th is so much greater than times 10 to the 8th, so it's pretty much going to stay the same, but we'll do it for completeness. So if we do this, we're going to have 6.67 times 10 to the negative 11th, mass of the sun, 2 times 10 to the 30th, mass of the moon, which is given above, is our 7.35 times 10 to the 22nd. Whoops, that's a 5. Times 10 to the 22nd, and then divided by the quantity, and this is the 1.5 times 10 to the 11th minus the 3.84 times 10 to the 8th. So 1.5 times 10 to the 11th minus 3.84 times 10 to the 8th. This number's not going to change a lot. We're just going to get 1.496 times 10 to the 11th. So it's pretty much still just 1.5 squared. That's how big these distances are. Like the small distance didn't really change anything. So now we just multiply all these together, and we're going to have 6.67 times 10 to the negative 11th times 2 times 10 to the 30th times 7.35 times 10 to the 22nd divided by parenthesis 1.496 times 10 to the 11th close parenthesis, squared that number at close parenthesis, and we get 4.38 times 10 to the 20th. So what we're going to have here is this going this way is 4.38 times 10 to the 20, and the amount of force pulling towards the Earth is the 1.98 times 10 to the 20. And since these are in opposite directions here, we need to make one of them positive, one of them negative. They're going to fight each other. We'll make the sun the bigger value, I guess. So that's positive, and then that means this going to the right is negative. So we're going to have 4.38 times 10 to the 20 minus 1.98 times 10 to the 20. And when we put those together, let's see, Since they're both times 10 to the 20, we can just kind of ignore it and just do the numbers. So 4.38 minus 1.98 gives us 2.4. And then we plug in the times 10 to the 20 again. So times 10 to the 20 newtons. And since that's a positive number, it's going in the positive direction or towards the sun. So it's just a lot of GMM over our squares and kind of figuring out what direction are the vectors pointing. Are they pointing to something? Are they pulling in a different direction? And then adding them together. So nothing too crazy, but that's what we're talking about. We're talking about forces for celestial bodies and looking at gravity in a complete total. Hope that was straightforward for you. The big thing is just calculators. It's easy to mess things up on this all the time, and if you're having calculator problems, take it one step at a time. Make sure you're using the E button for times 10, and just take it very slowly and be careful about squaring those R's in the denominator. But this one's finished. Adios. Take it easy. Bum, ba-dum, bow, bow, ba-dow.